Have you ever really thought about the magic box in your kitchen? You know, the one that keeps your food from spoiling? Or that blast of cold air in your car on a brutal summer day? It feels like magic, right? But it's not. It's all chemistry. A story about these invisible, hardworking chemicals that literally change the way we live. So, let's pull back the curtain and take a look. So yeah, how does it work? It's a really simple question, but the answer's pretty cool. See, a fridge isn't about making cold. It's all about moving heat. And to get how that happens, you have to meet the star of our show, the refrigerant. Okay, so what is a refrigerant? Just think of it like a heat sponge. It's this special liquid that has a superpower. It can turn into a gas and back again really, really easily. And that little trick, that phase change, is what lets it soak up all the heat from inside your fridge and just dump it out into your kitchen.
And this whole thing happens in a continuous loop, like a little dance. First, inside the fridge, the liquid refrigerant evaporates into a gas, and that's what absorbs the heat, making everything cold. Then, a compressor squeezes that gas, making it super hot. That hot gas flows to the coils on the back of your fridge, where it cools down and turns back into a liquid, releasing all that heat. Finally, an expansion valve cools that liquid way, way down, and the whole cycle starts over. It's brilliant, and it's happening in every air conditioner and refrigerator on the planet right now.
Now, for a long time, the chemicals that made this all possible were, well, they were pretty nasty. We're talking toxic, flammable stuff. But then, in the 20th century, scientists cooked up something that seemed like the absolute perfect solution. And that answer came in the form of a new family of chemicals called chlorofluorocarbons. Yeah, it's a mouthful, so we just call them CFCs. You've probably heard of their brand name, Freon. Refrigerants with names like R11 and R12 were about to totally revolutionize, well, everything. And I mean, just look at this list. On paper, these chemicals were absolutely perfect. They weren't poisonous, they wouldn't catch fire, they didn't eat through the pipes they were in, and here's the big one, they were incredibly stable. That meant they could just do their job for years and years without breaking down. It really felt like a massive win for modern chemistry. Or so we thought. Because while these CFCs were busy keeping us cool down here on Earth, their greatest strength, that amazing stability, was about to become their most dangerous, most terrifying flaw. So fast forward to the 1970s and 80s. Scientists looking up at the sky start noticing something wrong. Way up in the stratosphere, our planet's protective ozone layer, you know, the thing that acts like a global sunscreen protecting us from nasty UV radiation, it was getting thinner. And over Antarctica, a gigantic hole was literally opening up every single spring. Something was up there eating our atmosphere. So, the hunt was on to find out what was going on. And you'll never guess where all the evidence started pointing. Right back to our safe, stable miracle refrigerant, the CFCs. It turns out that incredible stability was the whole problem. See, CFCs didn't break down here on the ground. They just floated, unchanged for years, all the way up into the stratosphere. And up there, the UV radiation is so intense it could finally break these tough molecules apart. And when it did, it released a chlorine atom. And a free chlorine atom is like a tiny ozone-seeking missile. It slams into an ozone molecule, rips it apart, and then, and this is the scary part, it's freed up to go do it again, and again, and again. A single chlorine atom could destroy thousands of ozone molecules. To really get a handle on the damage, scientists came up with a scale. They called it ozone depletion potential, or ODP. The idea is simple. It's a score that tells you how bad a chemical is for the ozone layer compared to our original miracle CFC, R11. And this says it all, doesn't it? R11 wasn't just on the scale of ozone destruction, it was the scale. It was the benchmark, the definition of the problem, with an ODP of exactly 1. So the discovery was just terrifying. The proof was rock solid. Our technology was literally ripping a hole in our planet's shield. But what happened next is honestly one of the greatest success stories in human history. The world acted. I mean, really acted.
In 1987, countries from all over the globe came together and signed the Montreal Protocol. It was this landmark treaty to basically ban the chemicals that were destroying the ozone layer. And the craziest part? It actually worked. Production of the worst CFCs was stopped, and the ozone layer began the very long, very slow process of healing itself. But of course, the story doesn't end there. We banned CFCs, sure, but people still needed refrigerators and air conditioning. The industry had to scramble to find a replacement, a new way to keep us all cool without destroying the atmosphere. So say hello to the next generation, hydrofluorocarbons, or HFCs. The big difference? No chlorine. That was the key. Take R134A, which replaced the old stuff in car ACs. Without that destructive chlorine atom, its ozone depletion potential is zero. Zilch. It doesn't harm the ozone layer one bit. Problem solved, right? A perfect solution? Well, not quite. Because just as we were solving the ozone crisis, we were becoming aware of a whole other atmospheric crisis, climate change. And that meant we needed a new way to measure things. Global warming potential, or GWP. This number tells you how much heat a gas traps compared to carbon dioxide. And here's the gut punch. Our new HFC refrigerant, R134A, the one with an ODP of 0, it turned out to be an insanely powerful greenhouse gas, thousands of times more potent than CO2. We dodged one bullet just to run straight into another.
And this right here, this is the massive headache for scientists and engineers today. It's all a trade-off. The old stuff, R12, it worked great, but it killed the ozone. The current stuff, R134A, it saves the ozone but cooks the planet. And other options, like ammonia, well, they're perfect for the atmosphere. 0 ODP, 0 GWP, but they take us right back to square one. They're toxic and flammable. Finding that one magic chemical that's safe for us, safe for the ozone, and safe for the climate, that's the holy grail of cooling.
So, the story of how we stay cool is far from over. It's a pretty powerful reminder that sometimes the perfect solution to one problem ends up creating a totally new one you never saw coming. We as a planet came together once to save the sky. The big question now is, can we do it again?